Right, hello there. Welcome to everyone here and everyone online for our Friday lecture. Remember, every week or so, I'll be putting out a magic word. Magic word for this week is Hawaii. And you never know, maybe you'll be in the lab or somewhere and I'll ask, what's the magic word? And if you don't know, then I guess you haven't been keeping up with lecture, either in person or online. Oh dear, how uncomfortable. So Hawaii is our magic word for this week. Just looking at the viewing figures on YouTube, there's about 40 people who should be watching these videos, and yet regularly there's only about maybe 15 people who watch the videos. So I guess it's just too easy taking the class and listening to lecture. People need a greater challenge. So let's find out who those people are. Oh, excuse me. Right, so let's get started. So we had looked at the balancing of equations, we'd looked at the different classes of reaction, and we had looked at climate change on the online video from Wednesday. So now we want to switch tacks and start thinking about the mole. So far, when we've been trying to measure the mass of atoms and molecules, we've been just using the AMU, the atomic mass unit, given in the periodic table, which is an arbitrary mass for individual atoms, just a comparison. So when it talks about 12 atomic mass units for carbon compared to 24 atomic mass units for something like magnesium, it's just trying to say that a magnesium atom weighs twice as much as a carbon atom. But these are not real mass measurements. When we think about an atomic mass unit, which we attribute to either a proton or a neutron, in grams, that comes to 1.6 times 10 to the minus 24 of a gram, an incredibly small amount of matter, and certainly not something we could easily, even remotely, easily measure in a balance in the laboratory. Most of our balances go to just 3 decimal places, never mind down to 23 decimal places. So that is not really something that's appropriate. So just like you go to the shops and you buy some products in bulk, like eggs or potatoes, we measure the mass of chemicals in bulk. But instead of using a dozen to describe a standard unit, we use a mole. Now the mole is based on the mass of 12 grams of carbon. And this is something that Avogadro did. The legend goes that he actually counted individual atoms of carbon, as the legend goes. I don't think he quite did that, but he certainly did something very meticulous. And he found that in about 12 grams of carbon, we had 6.022 times 10 to the 23 atoms of carbon. And so he described this as being a mole of carbon, and a mole for any element. 6.022 times 10 to the power of 23 of those units or atoms. So why did he come up with such a strange number? Well, if we look at the math for it, taking for example, sodium itself, 23 units of mass, atomic mass units for a single atom. That's what the periodic table tells us. Now, if we multiply that mass in atomic mass units, we multiply it by the mass of an atomic mass unit in grams, the 1.66 times 10 to the minus 24. That initial calculation gives us the mass in grams for one single atom of sodium. If we then multiply it by the number of atoms to make a mole, the 6.022 times 10 to the power of 23, like taking the mass of one potato and multiplying by 12 to give us the mass of a dozen, that mass for a mole of sodium atoms is exactly the same as the mass for a single atom when we're using atomic mass units. So this was the clever device in Avogadro's plan. Using this particular bulk quantity, 6.022 times 10 to the power of 23, those values on the periodic table are now representative of molar masses in grams for each of the elements. So we don't have to design a new periodic table. The old one works, and those numbers in the table now describe molar masses. So we'll use those values given in the periodic table with just the odd caveat. And that is when we get to examples which have a decimal place in the molar mass, which is less than 0.1. We normally say that they're so close to a whole number, we're just going to round down to that whole number. So for example, hydrogen is 1.008 grams. And so we just round down to 1. Carbon is 12.011 grams, less than 0.1 of a difference. So we round down to 12. Sulfur is 32 point something. Let me check. I can't remember offhand what sulfur comes out as. Not that it's really important, but just for the principle. There we go. 32.07. So less than 0.1. And so we'll just round that down to 32. In a similar fashion, if the mass is almost all the way up to the next whole number, so 0.9 or greater, then we normally round up. Oxygen, 15.9998 grams, so we just round up to 16. Phosphorus, 30.9 something, let's check. Phosphorus, 30.97, so we just round up to 31 normally. Similar argument with things like, let's see, the arsenic, it is 74.92, so we'll just round up to 75. Any other good examples? There's a few in there. Aluminium, of course, 26.98, we normally just take as 27. So if the mass is almost a whole number, we'll round down or up as appropriate. And then the annoying ones which are in the middle, we consider that rounding down or rounding up to be too much of an error in our calculation. So magnesium, normally quoted at 24.3, and we'll leave it as 24.3. Chlorine, quite often quoted as 35.45, and so we'll treat it as 35.45. So those ones with decimal places between 0.1 and 0.9, we just leave them as is. So, if you want to know the total mass of a sample, we can use the chemical formula and the molar masses from the periodic table to work out the mass for 1 mole of that compound. And then, with the number of moles, work out the mass for that number. So the molar mass multiplied by the mass of the number of moles gives us the total mass. So for example, looking for 3 moles of water, just taking off the periodic table those masses, 1 gram rounded down for hydrogen times 2, 16 grams for oxygen rounded up, so that's 18 grams per mole. Our target is 3 moles, so 3 times the 18, that's 54 grams total. 4 moles of oxygen gas, remember that's O2, so 1 mole of oxygen molecules would be the 16 times 2, 32 grams. So 32 grams for a mole of oxygen, but 16 grams for a mole of oxygen atoms. And then 4 moles of oxygen molecules, 4 times 32, 128 grams. Hopefully no big surprises there. That's probably similar to things you've done in high school chemistry. Remember, a mole is 6.022 times 10 to the power of 23 of those units. So we can talk about fractions of a mole and still be talking about a whole number of molecules or units. Just like half a dozen eggs is still 6 whole eggs. We're measuring in bulk. So for 4.25 moles of nitrogen dioxide, we look at the chemical formula and the values in the periodic table for their molar masses. 14 grams for nitrogen, 16 grams for oxygen times 2, so 46 grams per mole. So the 4.25 moles comes to just under 200 grams at 195.5. Work out the mass of 1 mole and then multiply by the number of moles. Conversely, we can work backwards with a total mass of the compound and divide by the mass for 1 mole to work out how many moles we have. It's like taking the mass for, I don't know, maybe a number of eggs and dividing by the mass for a dozen eggs, we can work out how many dozen eggs are in that mass. So if we've got 112 grams of oxygen, that formula O2 tells us that 1 mole of oxygen would be 32 grams. So the mass in total divided by the mass for 1 mole gives us a molar equivalence of 3.5 moles. The propane, 420 grams of total mass. From the formula C3H8, we can take 12 grams for carbon times 3, 1 gram for hydrogen times 8, so 1 mole would be 44 grams. So that total mass, 420, divided by the mass for 1 mole that we've just worked out, that comes to 9.55 moles. 220 grams of the carbon dioxide. Again, work out the mass of 1 mole first, 12 grams for carbon, 16 grams for oxygen rounded up times 2. So that comes to 44 grams. So that total mass, 220, divided by the mass for 1 mole, 44, that comes to 5 moles. Oh, shit, I've got a drink of water before I started. Let's see. So when we look at the balanced equations, as we did on Monday, of course, that's talking to us about the amount of each chemical, which we initially thought was individual molecules, but those coefficients that we were using to balance the equation can now be thought of as molar equivalents as well. And it's just like a big cooking recipe when we look at a balanced equation. We've got a certain amount of each ingredient, and those ingredients combined produce a product, a certain number of cupcakes, like in this case. So 20 grams of sugar with 4 grams of salt, 100 grams of flour, 8 eggs, 10 grams of oil to make 8 cupcakes. You can probably tell I have no idea how to cook, just throwing in these values. But the important thing here to remember is that just like any cooking recipe, which you can scale up or scale down if you want to make a greater number of cupcakes or a smaller number, what we're going to look at next is that we can scale up or down the equation that we're using for greater or smaller amounts of each product. Oh, looks like Maria got kicked out briefly. Let her come back in. And Maria's back. So just like any cooking recipe, which we can scale up or scale down, we can do the same thing with a chemical reaction. So let's say from our cooking recipe, one day we only had 10 grams of sugar. Oh no, that's only 50%. That can still work for us if we use half the amount of salt, just 2 grams, use half the amount of flour, just 50, half the number of eggs, 4, or half the amount of oil, 5, and we'll produce half the number of cupcakes. Or if we had 40 grams of sugar and we wanted to use it up to make as many cakes as possible, of course, compared to the original recipe, 20 grams, that's twice as much. So we'd use twice as much salt, flour, eggs, oil, and produce twice as many cupcakes. I'm sure you get the idea. And we've got all versions in between. So if we've got 75% of the sugar, 15 grams instead of 20, we could use 75% of the salt, flour, eggs, oil, and make 75% of the cupcakes, 6 instead of the original 8. We can work out any manner of proportions, greater or smaller, as long as we have a plentiful supply of all the other chemicals or materials being used. Let's look at this in the terms of an actual chemical reaction. Whoops. So, reaction between ammonia, NH3, taking 4 moles at a time. That's reacting with 5 moles of oxygen gas normally, 4 moles of nitric oxide, and 6 moles of water. Again, these proportions are just the lowest whole number proportions we can get. So if someone else is trying the same reaction, they come to the same proportions, the same balanced equation that we do. And so everybody's working on the same page. But that doesn't mean that we can't work with larger proportions or smaller proportions. We just have to adjust everything, just like you would adjust that cooking recipe in the cookbook. You're not forced to make 8 cupcakes if they're just cupcakes for yourself, although mind you, can you really have too many cupcakes? That's the question that burns through every scientist's mind. So we've got molar proportions here, but we have to work out those moles into mass proportions. You're not going to weigh moles on a balance, you're measuring mass. So with a periodic table, we can convert those molar amounts into mass amounts. Give me 1 second, because I think Netflix has stopped working for my daughter. 1 sec. Hi, baby. Did it switch off? Right. Okay. So no real problem other than the fact that she was rolling around on the bed, on a bed that she'd covered in cheesy puffs and had made a big mess. That girl takes after her mother. Okay, so with a periodic table, 4 moles of ammonia, we can work that into a mass of ammonia. We've got 14 grams for nitrogen, 1 gram for hydrogen each time, so 17 grams per mole. So 4 moles, 4 times heavier would be 68. The 5 moles of oxygen becomes 160 grams. 4 moles of the nitric oxide is 120. And 6 moles of water comes to 108. So those molar proportions can be converted into mass proportions. Notice also that the total mass that goes into the reaction is equal to the total mass that comes out of the reaction, 228 grams. Just as we talked about in chapter 1, we've got conservation of mass with these balanced equations. So if we were trying to perform the reaction with a different amount of ammonia, let's say just 34 grams instead of the 68 that we normally use, that's just half the amount, that's just 2 moles. So with a 50% capacity for ammonia, we could only use 50% of the oxygen, 2.5 moles instead of 5. We'd only produce 50% of the nitric oxide, 2 moles instead of 4, and 50% of the water, 3 moles instead of 6. So if we know how many moles we have of one of the reagents, assuming we have an excess supply of everything else, on a molar scale, we can work out these reduced proportions. Or if we've got 12 moles of ammonia instead of 4, that's 3 times more. So we'd use 3 times the amount of oxygen and produce 3 times the amount of nitric oxide and water. You get the idea. 10 times more, we use 10 times more of each material and produce 10 times more of each material. Any questions at this point? Doing okay? Depends how comfortable you are with math, I think, this chapter. Some people dread chapter 5, but some people get really excited about it because they understand numbers. So if we look at an example, the kind of thing that might pop up in a chapter 5 homework or exam, we've got the original balanced equation, 1 mole of nitrogen reacting with 1 mole of oxygen to produce 2 moles of the nitric oxide, NO, which we of course would call, nitric oxide is a common name, but we would refer to it as nitrogen oxide using nomenclature theory. So you're told that you have 224 grams of nitrogen, an actual mass figure because somebody would have measured that in mass. You wouldn't have measured the number of moles on a balance. So we've got 224 grams of nitrogen. How much oxygen would we use with it, and how much of the nitric oxide would be produced? So that's the information we have so far, 224 grams of nitrogen. But of course, our balanced equation is talking to us in molar quantities. So we need to turn that 224 grams into a molar quantity if we want to relate it to the balanced equation. So of course, nitrogen, that's N2, 14 times 2 from the periodic table. So 28 grams per mole. And just as we did in those earlier calculations, we take the total mass, 224 we're being supplied with, divide by the mass of 1 mole, 28, which we just worked out, and that comes to 8 moles. So we've actually got 8 moles. Normally the equation, that original reaction, uses 1 mole. We've got 8. So we've obviously got 8 times more. You've got the calculated number of moles compared to how much are used in the original equation, 8 to 1. So we've got 8 times more nitrogen than we normally have. And to keep the equation balanced, we'll apply that to the whole equation. 8 times more nitrogen. So we'll use 8 times more oxygen, 8 moles, and 8 times more of the product, nitric oxide, so 16 moles. So those relative proportions, 1 to 1 to 2, are still there. It's now expressed as 8 to 8 to 16. This is an important line in the sand to get to. Work out the new proportions for your reaction. 8 times greater, so 8 to 8 to 16, and write that down on a scrap piece of paper. You can now, using a periodic table, work out the mass for these new adjusted proportions. So for the oxygen, 1 mole of oxygen gas, of course that's 16 times 2, 32 grams. So that new target of 8 moles would be 256 grams. For the nitric oxide, normally the reaction produces 2 moles, but we had 8 times more nitrogen, so we needed 8 times more of everything else. So now the 16 moles is the target, For the nitrogen, that's 14 grams per mole. Oxygen, 16 grams per mole. So 30 grams per mole. Our target is 16, and so that's a total of 480 grams. And that makes sense because the total mass going in, 224 plus the 256, must equal that total mass coming out from just the nitric oxide. So we've used a mass of one of the chemicals, turned it into a molar quantity. That implies a particular number of moles of all the other chemicals, and then using the periodic table, we can work out the mass for those chemicals. Let's see, how much more should we do? Yeah, I guess we can do a little bit more. Making good progress this week, but a bit more I think would be good. So looking at the next one with the nitrogen reacting with hydrogen to produce ammonia, NH3. This is a very important industrial process. It's a billion-dollar industry making ammonia, which is often used by farmers around the country as a main fertilizer. Let's see, so if we had 136 grams of ammonia, so we're being told how much of the product has been produced this time. If it's 136 grams produced, how much nitrogen and the hydrogen were used to produce that amount? Okay, somebody wants to play Minecraft. So we know the target, how much is actually produced, how much of the ingredients did we use to make that happen? Well, again, the equation is talking to us in molar quantities, so that mass has to be turned into a molar quantity. Of each of these problems, that's usually the first task, work out the number of moles. Then we can apply that to the equation. So for NH3 ammonia, that's 14 grams for nitrogen, 1 gram for hydrogen, rounded down, so a molar mass of 17. For the number of moles, we take the total mass divided by the mass of 1 mole, that comes to 8. Now compared to the original product quantity, 2 moles, the 8 moles that we have is 4 times more. So we've calculated that the 136 grams is 8 moles. The equation normally produces just 2 moles. And so we can see we've got a multiplier of 4 times. If we produced 4 times as much of the ammonia, we must have used 4 times more of the nitrogen, 4 moles instead of 1. And we must have used 4 times more of the hydrogen, 12 moles instead of 3. So this gives us a new adjusted proportions, the new multiplied proportions. And so with those figures, we can then work out the mass for those adjusted molar amounts. So the nitrogen gas, 14 grams for nitrogen. Nitrogen molecules, N2, that will be 28 grams. 4 moles, our target, 4 times the 28, that comes to 112 for the total. One sec, guys. All right, that should keep them busy until we get finished. So we needed 4 moles of nitrogen instead of the normal 1 mole, and that comes to 112 grams. Just the amount of hydrogen needed now. From the chemical formula, of course, 1 gram for hydrogen atoms, 2 grams for a mole of hydrogen molecules, H2. And so a target of 12 moles, that comes to 24 grams. And it gives us our final answer. The 112 plus the 24 does come to the 136 we had originally said was produced by the reaction, which was 8 moles. Any questions about that one? Doing okay? Everybody's asleep. Okay, let's see. We'll make this our last page, I think, this one today. So that at least gets us into some examples. So this is a kind of shorthand one, a bit more brief, but I'll walk through it. Reaction with sulfur dioxide, combusting in oxygen. We know it's a combustion reaction because it's being reacted with oxygen gas to produce sulfur trioxide. There's another class of reaction that we could put this reaction into. We can think about it as combustion, but we could also think about it as a, anybody know? Silence. Somewhere in the distance, a dog barked. No, we've been too shy. We are muted. You're muted. How did you become muted? Okay. I thought you were just being shy. Oh well. No matter. I'll figure that bit out later. So I'm sure someone was about to say that it could also be described as a combination reaction. That's weird. Why does it do that? Whoops. Somebody's got their voice back.
I just unmuted myself.
Okay. I'm not muted, I presume. Okay, because that would be bad. So the sulfur dioxide combining with oxygen in a combustion reaction to produce sulfur trioxide. If we had 512 grams of the sulfur dioxide, SO2, how much oxygen would we need to react with it, and how much sulfur trioxide would be produced? Well, we need to turn that mass into a molar quantity because our equation is talking to us in molar quantities. 512 grams, 1 mole would be 32 grams for sulfur, with the 16 grams for oxygen times 2, giving us another 32. So 64 grams per mole. So that mass divided by the mass of 1 mole comes to 8 moles. Normally we're using just 2, so the 8 would be, again be an example of 4 times more. So we need 4 times more of everything else. 4 times more oxygen, so 4 moles. We'll produce 4 times more of the product, so 8 moles. And that gives us our new proportions for the reaction, the new scaled up proportions. So oxygen, that's 16 grams per mole of oxygen atoms. O2, oxygen molecules, that would be 32, times 4 gives us the 128. Sulfur trioxide, 32 for sulfur, 16 for oxygen times 3. That gives us a mass of 80 grams per mole, multiplied by 8, a mass of 640 grams. Let's try one more before we call it a day. We are ahead of the sister sections by a little bit, but as soon as we've started this, let's keep going. So don't worry about the second one, just think about the first one there. Take a couple of minutes and see if you can come up with the mass amounts for oxygen, carbon dioxide, and water if we used 180 grams of ethane, C2H6. Remember, lab experiment next week will be experiment number 8.
I'm not sure what she's doing, but she's supposed to be that way. I was going to text her something about what she gets back.
Remember, our first task is just to work out how many moles 180 grams of ethane is, and we can use the chemical formula for that, C2H6, excuse me. We have, from the periodic table, 12 grams for carbon per mole. For hydrogen, we've got 1 gram per mole. So 1 mole of ethane comes to 30 grams. Now we've got 180 grams in total, divided by that mass of 1 mole, 30. So the number of moles is 6. Now compared to the original amount in the original equation, 6 compared to 2, we've actually got 3 times more. If we're using 3 times more ethane, we're going to have to use 3 times more oxygen, and we'll produce 3 times more of each of the products, carbon dioxide and water. And so it's a good idea to write out the equation in these new proportions. So the 6 moles of ethane that we know about, which was 180 grams. We've now got 3 times more, 21 moles of oxygen gas, 3 times more, 12 moles of carbon dioxide, and 3 times more, 18 moles of water. write down the new equation in its adjusted form. That helps to avoid getting lost in the equation because we've got lots of numbers flying around here. So just oxygen, O2, that'd be 16 grams times 2. So 1 mole is 32 grams, as we've mentioned a couple of times already. The target is 21 moles. Let's see, 10 would be 320, 20 would be 640, plus another 32, 672. I usually like to put the total mass for each chemical used or produced in a circle, so it just kind of highlights it compared to the other numbers you have flying around. You don't have to do that, but I find it's helpful. You might too find it helpful too. So at 21 moles of oxygen, that's 672 grams. For the carbon dioxide, it's 12 grams for carbon, 16 grams for oxygen times 2. So 1 mole becomes 44 grams. Our target is 12 moles. Let's see, 10 would be 440 plus another 88. So 528, I think that is. For the water, 18 moles, again 1 gram for hydrogen times 2, 16 grams, whoops, back up, not multiplying, just add another 16 grams for that oxygen. So 1 mole of water is 18 grams per mole. Always work out the mass of 1 mole before you work out the mass of a larger quantity or smaller quantity. The target is 18 moles. So 10 would be, let's see, 180. The 10 would be 180, so 360, subtract 36. 324, I believe that is. Going blind without my calculator, although it is here, so let me check that. Just to be absolutely sure. Total mass in should equal total mass out. So the 180 plus the 672 looks like comes to 852. And that 528 plus the 324, 852. Yes. So total mass then equals total mass out. Okay. Any thoughts or questions before we finish?
Nope, all good.
All good? Okay. Yeah, we can stop there. We have made definitely enough progress. Woohoo! Finished class 2 minutes early. Wow, that's fantastic. Best class ever. Have a good weekend, guys. Remember, online chance to take the exam tonight at 9 o'clock and then Sunday at 9 o'clock. Some people have written to tell me they intend to take the exam tonight to ease up on the Sunday night queue online. So maybe it'll be fine on Sunday. And the exam is in the learning lab this afternoon. I think they close by 4 o'clock on a Friday. It is earlier than usual. And you do have to be in there an hour before they close. They won't let people start with less than an hour, okay? You left Cheetos on my bed, did you? Okay. Was that a special present for me? No. No? Okay. It was a trick? Oh, you are tricky. Right. Say bye-bye. No? Okay.
Bye.
Bye. I'll say bye for you. No, don't go. Let's do another hour of chemistry. Everybody stay where you are. This is stampeded for the exit. More chemistry. Why are people disappearing? More chemistry. I can't see, baby.